All right, guys, we are still looking at lesson 8.2, the natural base e, and we're going to create an equation for a transformation of f of x equals e to the x power. All right, so this is task 3. Given the graph of g of x equals a times e raised to the x minus h power plus k, you can write this equation using the reference points h, comma, a plus k, and h plus 1, comma, a times e plus k. Write the equations of the exponential function with base e shown in the graph below. The 2 points shown on the graph are the reference points. All right, so you can see they have given you the horizontal isotope, that's y equals 1, and they've given you 2 reference points, 3 1/2 and 4 comma negative e over 2 plus 1. All right, it says use the isotope and the given reference points to find the parameters. Use the isotope to identify k. The isotope is y equals 1, so k equals 1. All right, so with the parent function, we know that the isotope is y equals 0. So since the isotope here is y equals 1, we know that's going to affect our k, which is our vertical movement or our vertical translation. Which of the following represents the relationship between k and the horizontal isotope of an exponential function? The horizontal isotope equals negative k. The horizontal isotope equals k. The horizontal isotope y equals k. Okay, so the x's we know it can't be. So it has to be either the first one or the third one, and we know it's not negative. So it's just going to be y equals k. All right, how can you explain the connection between k and the horizontal isotope? All right, so k again is your vertical movement. Okay, so when the isotope moves up to y equals 1 from 0, we know that k is what caused that vertical movement, that shift up 1. All right. Use the first reference point and k to find a and h. The first reference point is h, comma, a plus k. And we know from the graph that's 3 1/2. So again, that's just given information. We've got 3 1/2 here on the graph. And so we're going to set that equal to what we know the formula is. So h equals 3 and a plus k equals 1/2. All right, so that makes it very easy to find h. And then we have to do a little bit more. We already know what k is. K was equal to the vertical or the horizontal isotope. So that's your vertical movement there. So we can find a knowing h and k. All right, so it says how do the coordinates of the reference points help you find h and a? All right, so the x value of the reference point represents some shift of the transform function. So that's your horizontal shift. And the y value of the reference point shows the sum of the horizontal and the vertical translations, the vertical stretch and the vertical translation, the horizontal. All right, so we know that that's going to be the vertical translation because a is your vertical translation and k is your vertical shift. So let's see. Vertical stretch and vertical translation. All right. And again, what they did to find a, we already knew that k was equal to 1. Okay, again, that's from the graph. We know that the isotope is equal to k. So y equals 1, k equals 1. So given that k equals 1, we can just plug that in to find a. So a plus 1 equals 1/2. Subtract 1 from both sides, you get negative 1/2. And that makes sense as well. If you look at the graph, it is a reflection. It's upside down. So you know it has to be negative. And then you can see that the shape has changed a little bit too. So that's where the 1/2, the vertical compression comes in. All right, what would your work look like if you used the second reference point to find h and a? The second reference point is, all right, so this is what you have given. So we're going to do 4 equals h plus 1. So subtract 1 from both sides, h equals 3. And then you're going to let negative e over 2 plus 1 equal a times e plus k. And substitute in what you know from that. And you know that k is equal to 1. And you can plug in, let's see, you subtract 1 from both sides and just have a times e equals this other side here. And then when I divide by e, it's going to cancel that out, and that just leaves a equals 1/2. So that's just solving for a. Remember, e is a number. It is a variable, but in mathematics, e represents the number 2.718. All right, write the equation g of x equals negative 1/2 e raised to the x minus 3 power plus 1. All right, it says, how could you use your understanding of transformations in the parent function to check your equation? Match each feature with the equation of the transformation it represents. All right, so this one says the parent function shifts 3 units to the right. Okay, so that's your horizontal movement. Shifting left or right is your horizontal movement. The parent function shifts 1 unit up. That's your vertical movement, so that's your k. The parent function undergoes a vertical compression by 1/2. All right, a vertical compression by 1/2. That would be your a value. And the reason it's in absolute value, because if this is a fraction, regardless of whether it's positive or negative, it creates that compression. And then the parent function is a reflection. That's because it's less than 0. So that's where the negative comes into play. All right, that's all for task 3. If you have any questions, let me know. 8.2, task 4. Model a real-world situation using an exponential function with base b. Transformations of the exponential function f of x equals e to the x can be used to model real-world situations involving exponential growth or decay. The value of e is greater than 1, and therefore the general formula represents exponential growth. However, you can use the property of exponents to write g of x equals e to the negative x, which is the same as 1 over e to the x, which represents exponential decay, since 1 over e is between 0 and 1. All right, carbon-14 is a radioactive isotope of carbon that decays at an exponential rate. The percent of original carbon-14 in a fossil after t years can be modeled by n of t, where t is the number of years after the specimen died. What is the decay rate of the function? What is the age of the fossil? All right, so it says a fossil contains 16% of its original carbon-14. All right, so you can see the specimen they're digging up out of the earth right there. They're just kind of being very careful with it because they want to make sure they don't damage it when they're bringing it out of the ground. All right, so it says find the value of r. All right, so here's our equation, n of t, and you can see that it's e to a negative exponent, so that's going to be exponential decay. And then let's see what it asks. So how is the form of the equation related to the exponential decay formula? The parent function for exponential decay is anything to the x power. Remember, b to the x power. Exponential decay, your variable is your exponent, where b is between 0 and 1. So anytime it's decay, it's a fraction. Since e to the negative exponent equals this, that's below 1, the function represents decay. All right, it says set the base of the function equal to the base of the exponential decay formula and solve for r. All right, so it has e to this negative exponent here equals 1 minus r, your interest or your rate, decay rate in this case. All right, so for this formula, it's going to be e raised to the negative 0.00012. All right, so if you put this in your calculator, you can see that it's going to give you this. It doesn't give it to you straightforward. So if you, let me turn it on here. All right, so you got to be careful how you type it in. I typed it in incorrectly the first time, and you can see it gave me an error. And everything with your calculator is about how you enter it. So if I enter 1 minus e raised to the negative, and I put this in parentheses just so it knows e is to that whole power, and then it gives me this. And this e to the negative 4, this is just in scientific notation. This tells me that I have to move my decimal place to the left 4 places. So if I go to the left 1 and then 3 more times, I've got 0.30012. So that's where this 0.00012 comes from. It's just when you use your calculator to determine that, it'll show up like this, which is, again, in scientific notation. If you have questions about that, please let me know. All right, moving on. Find the age of the fossil. Use a graphing calculator to graph the function n of t and the line n equals 16 on the same coordinate plane. Remember, n equals 16 is 16% of the original carbon-14, okay? All right, so it says, how does the line n equals 16 help you find the age of the fossil? All right. Let's see what their explanation is, because they probably can explain it better than I can. It's going to be the decay rate after so many years, but that's when there should be about 16% of carbon left. So it says the line n equals 16 represents a value of 16% of the original carbon-14. So the intersection point of n equals 16 and the graph n of t gives the time in years when 16% of the carbon-14 remains. Okay, so this is your function, and then this is n of 16, and you can see the intersection point here. All right, so it says, what does the point 15,271 and 16 represent in the given content? All right, the intersection point represents after 16 years. Now, we just said the 16 is the 16% of carbon-14. So the intersection point represents after this many years, there is 16% of carbon remaining. That is correct. The intersection point represents that after there is about 16 grams. No, we weren't talking about grams at all. All right, so the value of the function is 16 when t is approximately 15,272 years. So the fossil is about 15,272 years old. All right, that's all for task 4. If you have any questions, please let me know.